have you all come to the, yes. Thank you so much for waiting and welcome to the first edition of CodeUp in Bandyopadhyay, Goa. We are very much delighted to be here and I'm Mansa, I'm your host for the evening. I hope I'm clear, I hope it's not, the voice is okay. So PayU, as you all know, is one of the leading payment service providers across sectors like airlines, SMBs, and of course the startup community. So, as a part of PayU's startup outreach program, we have two series that we do. One is UpStart and one is CodeUp. So we had our first series of UpStart in Goa around 3 months back, and it was a huge success. Again, all thanks to you guys, and of course the 91 Spring Board community. And today is our first CodeUp session. So CodeUp is a series where we bring in domain experts to talk about various topics, maybe relevant, maybe trending, which we want the people to know and discuss. And today's topic, we are talking about evolution of IoT, AI and ML. So our speakers lineup is pretty great. So our first speaker for the evening is Ashutosh Kumar. He's the head of DataScience at Seynse Technologies Private Limited. Our second speaker for the evening is Maddison. He's the founder and CEO at GIE and the director of ML, AI and data at Numadic. Our third and fourth speaker for the evening is Utkarsh Apoorva. He's the head of product, and Anubhab Bandyopadhyay. He's the head of technology at HandyTrain. We have a fifth speaker, Ashish Saraf. He's the CTO at TempoGO, and our final speaker is Rohan, Verma, founder Infidreams and director at MapmyIndia. So we have people from data science, we have people from ML, we have people from IoT. I hope you guys have a great session today and take back as much as possible. What we are going to do is, since we have a lot of speakers and we do not have enough time, we are going to limit the questions to probably one or two. So you ask the first or second question, you are done, or else we are going to keep you up for the networking session. I hope you people get that. I hope it's okay with you guys. So without further delay, calling upon Ashutosh, and a huge round of applause to you guys and him as well. Thank you so much.
Hello everyone, good evening. Thank you for being here, and a big thank you to the organizers, PayU and the ecosystem partner Prototyze and 91 Spring Board. As the theme of the session is evolving AI and IoT, I'm restricting this talk to evolution of the lending industry with AI. As in specifically in the lending industry, what was the state earlier, how the data has evolved, how the algorithms have evolved, and what are the things that are being done in this industry, in terms of this field of data science. A little bit about myself first. I'm Ashutosh Kumar. I'm currently working in Seynse Technologies, which is a part of the Prototyze Ventures, Goa. I've been working in the fintech space for the last around 2 years, and the part of my job requires me to build mathematical models on data to predict the creditworthiness of a customer. As in the business is, I'll come to that. We are in the business of providing credit to the customers after underwriting them on the basis of their risk and their data. I've been working in this field for around 10 years, close to 10 years. At that time it was called data analytics, now it's been called data science. In the few years it will only be AI, but it's the same thing. A little bit about the company which I work for. We work in the fintech and lending space. Started in 2016, it's a part of the Prototyze Ventures. We operate lending as a service as a platform. We enable the technology, we enable the backend, we enable the sort of the data science, technology, operations in every part of the business. we don't lend as on our own. We are not an NBFC, but we enable the NBFC and banks provide loans to the customers. We have a partnership with Airtel, which is our strategic partner, and Airtel is also an investor in our company. We have access to huge amount of data with Airtel, and in the later part of the discussion, I'll come to that, how this partnership is helping us, how we are using the telecom data from Airtel to build our credit models. LoanSync is our brand through which we lend for personal loan business. In case anyone wants to avail a loan, just go to the SAP website and avail the loans after providing the data, and the models will score the customer. We have a certified plus member team in Goa and Gurgaon. The proposition is credit with alternate data based credit models. What is alternate data? That's covered later in the presentation. We have a patent pending credit model algorithm. So, a little bit about the lending industry in India, just to set the context. What problem we are going to solve? It's totally based on the challenges that the industry is facing in India. Lending is a huge market in India. It's estimated to be roughly around 40 billion plus minus 10-15%. The numbers are not exact, but market is so big. Alternate lending space, which is where the NBFC comes in, which is where the unorganized market players comes in. That is currently 241 billion in 2018, growing at 53% CAGR and estimated to be $1.3 billion market by 2022. There is another thing which is called the credit to GDP ratio. Now, this ratio defines, how much of the GDP is the part. I mean, what's the part of credit is how much part of GDP. In the developed countries like USA and UK, this ratio is close to 90% or even 100%. In countries like India, it's close to around 20 to 25%. So there is a huge headroom for growth in this specific market space. In India, most of the organized lending is done by banks and NBFCs. Unorganized lending are done by money lenders, small credit providers, people who give credit in the morning, take it back in the evening maybe to the rural box or the retailers, the small shops. Everybody requires credit. This market is dominated by banks and unorganized lenders. There is very high interest rate for unsecured and unverified borrowers. There's another thing called credit bureau penetration. So, how many of you are aware about the credit bureau CIBIL? Yeah. So, CIBIL essentially looks at your historical data and scores you based on your past repayment pattern, based on whether you have made a loan in the past, how timely payment you have made. How much, if you have not paid any specific installment, your score will go down. And banks look at this score to provide you a loan. Now, this score is available only for 25 to 30% of India's population. So, there is a bunch of population, 70 to 75% of the population. It's either new to credit, or it has no previous repayment data, or they are unbanked, they don't have any bank accounts. And this population has a difficulty securing loans from any bank or any financial institution. So this part is a huge market which a lot of companies are trying to capture. So this is the challenge here is that these people don't have any data. How do you figure out whether this customer is good or bad, whether he is creditworthy or not? If you give a loan to this customer, whether he will come back or not. Solution is technology and data science. In the lending as a service platform which Seynse Technologies operates, there is minimal to no paperwork. It's heavily technology enabled. Every part of the traditional loan process is enhanced by technology. I'm not going to cover technology here because it's a huge space in itself. I'm mostly going to cover about how data science helps in this particular space. We now have advanced data science modeling, machine learning models to assess the creditworthiness of a customer. Earlier, it used to be done by the banks looking at very few variables, that whether the customer has taken a loan and paid in full, then he is a creditworthy customer, otherwise he is not. Or they go for secured lending, where you have to pledge in some collateral to get the loans. Now we don't need historical financial data of consumers. We also use a variety of other data sources. That's what I mean by alternate data. There is a huge amount of data available for every person in this world. You have your telecom data, utility bills data, you have your tax data. Every data can be used to create credit models for customers who don't have their credit bureau score. Also, this platform, this lending as a service platform, can be used by other banks or NBFCs to partner with the last platform provider, and they can also make use of this platform. A little bit about the data, because data is the essential part of data science. In the old age lending, how it was done earlier, banks normally, even now, they use the historical financial data. They have the data of customers who have been banking with them for a long time. They have sort of collateral information. If you have pledged your, say for example, gold or any property for willing a loan, they have information for that. They rely heavily on the bureau score. This is essentially based on the repayment pattern. What we do is, in the new age lending, we use this existing data, which is already available for a lot of customers, plus we make use of alternate data. Now, alternate data would be things like age, address, education, lifestyle, employment, company, college, and a bunch of other information. Just to give you an example, say for example, the model might predict that a person who is from a tier 1 college might have a lower rate of default or a lower probability of default than the customer who is from a sort of tier 4 college or something like that. Just to give you an example. Or a customer who is working in a very good company which is financially stable, the company is paying salaries on time. That customer has a lower risk propensity as compared to another customer who is not working in a that great company. So these things are decided by the model. These things are scored by the models, and the data is provided by us. There are other sets of data which we have. One is the bank statement narration. You have items in your bank statement. We have developed models which can figure out from the narration something like what part of your salary you spend in cash, or how much do you withdraw every month, or how much you spend on online, how much you spend on travel, how much you spend on entertainment. All this goes into your building your profile, which is used to predict your creditworthiness. You have things like utility bills, online data, app usage data. So the objective here is that the credit bureau information, this data is not available for everyone, but alternate data is available for a majority of customers. It's available for roughly 70 to 75% of the target market populations. So that's where we want to focus our strength. This is just an example of the publicly available data source. This is how some of the companies have started, scoring customers. If you look at the data points, you will find little, some weird things. Age of the car, that's also a data point. Something like, what is the family status of the client, or how many family members does the client have. Something like, what is the amount receivable on previous credit, balance during the month. So it's a combination of financial data as well as non-financial data. You might think that this data, how can this data be used for, assessing customers' risk? But these are just the indicators. They might or might not contribute to your credit score, but they essentially go a long way in building your credit profile, credit risk profile. Any questions? No? So, how our algorithms make sense of this data? The first thing is we need to get the right data in terms of value, in terms of volume. You can't just have millions of data which doesn't have any qualitative basis. It has to be a qualitative data. Also, it's a combination of supervised and unsupervised learning algorithms. More often than not, we don't get a 0 and 1 classification. We don't get a target variable in the models. So the first challenge here is always which is the target variable that we need to focus on. What is our 0 and 1 in this case? It depends on use case to use case. It depends based on the business proposition. Also, we need to validate the model. We cannot just take in some random data, build a model, and say that this is the best model. We need to validate it with the existing market practices. Also, it needs continuous monitoring and update because the data changes, the data sources changes, and it's not a sort of finalized model or a token model which should always be correct. It keeps on evolving, it keeps on changing. So we need to continuous monitoring and update for these models. Okay, so that was the context. Now I will talk about the use case that we have solved in Seynse technologies. in partnership with Airtel. Can your telecom behavior assess your credit worthiness? This is a problem that we have solved. The objective here is that every person will not have their credit bureau data, but everybody has a phone. In terms of mobile phones, India has 75% mobile penetration right now, which will go to 85 to 90% by 2020, with over 1 billion devices. 26% customers are on smartphone, and 4G data usage at 11 GB per user per month. So almost everyone has a mobile phone. Everyone uses that. The problem that we are trying to solve is, can we profile customers based on their telecom usage data? Your telecom behavior tells a lot about you, how much you are, whether you are paying on time, what's your mode of payment, whether you are defaulting on payments or not. Even things like how many calls you make, what is the network in which you make the calls. There are a lot of information. I'll get to those variables, what all we use for the model. There are some of the other companies in the world which are working on the same problem. There is Tala in Africa. They were the pioneer in this field. They essentially look at your phone data, SMS data, and figure out whether you are worthy for a loan or not, how much amount should be given for the loan. Then there is Just Finance and Lendo, which are key players in the US and UK, European markets. Trusting Social is a company which is in the Southeast Asia space. They all work on a similar type of data, which is the alternate data, not the non-traditional way of building a credit scoring models. This is just a news clipping from Bloomberg. No credit history, no problem. Lenders are now looking at your phone data. So the question is, how do they look at the phone data in such a way that to figure out the creditworthiness? The answer is here. Starting with the data, what type of data do we collect for solving such problems? So the first point is, we don't use any personal data, no call data records, no SMS data. Customer privacy is paramount. It's not being compromised anywhere in any way. The type of data we use is something like what type of phone you are using, how many circles do you roam in a month, whether you are staying in the local area all the time or you are going from one city to another city. That tells something about your profile. Do you use data mostly or mostly use voice calls? There are different types of customers who use data, different types of customers who use only calls or maybe SMS. Do you pay your bills on time if you are a postpaid customer? What mode of payment do you use for recharge or payment? If you are an online selling customer, you will obviously go for online recharges. If there are customers who go for 10-20 rupee recharges every day, they will use it, they will exhaust it, and then go for a recharge again. So the idea is to identify different types of customers using these parameters. Something like how long have you been using your phone? Something, say for example, if you are using an iPhone for say last 6 months and you are changing your phone frequently, that tells something about your profile. That you might have a good amount of money that you are rotating models every 6 months. And there are over 100 other variables. These are not the exclusive list of variables. There are over 100 variables. There are derived variables. There are variables which come from the additional sources. All of them go into the model. What models we have developed for them? The first part is define the business problem which we have. Data availability has to be ensured, whether the data is available for the customers or not. Actually, since our partnership with Airtel, we have a lot of data. They are the second biggest, telecom player in India. They have data of 300 million customers, which is something like 25% of India's population. One model doesn't work here. We have used an ensemble of multiple models. We have used logistic regression, decision trees, random forest, support vector machines, XGBoost for classification. We are currently in the process of deploying deep learning and NLP models. As the theme of the session is evolving AI and IoT, we are also evolving our models. Started with a basic model, now we have evolved to a deep learning based model. The stack that we use is essentially Python, Keras, TensorFlow, SAS, we also use SAS, though it's getting old, and Hive and Hadoop. I won't go into details of these models because it will take a lot of time. In case anybody needs to know in detail, please feel free to contact me after the session or contact me by email or phone, anything. I'll be happy to discuss the details. It's just a flowchart of how, not a fluent. Anyways, just a standard workflow of how we actually build the models. take the data, you take the alternate data, create a signal first, split the data into train and test, build models, score, validate, that's it. Now, why we chose the specific models and what are the benefits of each model? Logistic regression essentially gives you a probability of 0 and 1. You define your dependent variable, and this model will give you a probability of whether this customer, what is the probability of default of this customer. This is prone to overfitting if you have a huge amount of data. You deploy a ridge or lasso regularization to reduce the overfitting problem. Decision trees are also a very good approach to solve this problem. The advantage of decision trees are they give you very specific rules, and in our industry, in lending industry, it's very important because the regulators actually want to know why this particular loan has been rejected or has been approved. You won't get that from a deep learning based model. You won't get that from a neural network. But a decision tree will tell you, what are the rules that led to the approval or rejection of this customer. We also deployed the sample and boosting models, Random Forest and XGBoost. Let me know if anybody needs the details of these models, how they work in this specific scenario. I won't go into the details, but things like Random Forest, how Random Forest works is if they build thousands of different models and they vote on the majority class. This is something that we are trying right now. The deep learning based models using neural networks, LSTMs. We have access to a huge amount of data, and in case the data, if you have sufficient data, neural networks will always outperform your standard models. We are trying to build this particular model right now, wherein not only we are predicting the 0 and 1 class, we are also predicting whether what type of credit limit the customer can access to. For example, we are offering credit from 5,000 rupees to 50,000 rupees. With a multi-class classification model, we can figure out, okay, this is a bunch of customers who have a high probability of not defaulting on a loan of 5,000 to 10,000. This bunch of customers have a high probability of not defaulting on, say, 20,000 to 40,000 loans. So these are some of the ways where we are building the multi-class classification models using neural networks. The LSTM models are being deployed for sequential data. We have data of, say, repayment data, and we can deploy these LSTM models which have a very high accuracy, so that we understand that based on the previous pattern, when is the customer going to repay the loan, or whether he is going to or not going to repay the loan. That's where the sequential model comes into question. Any question on the modeling part of the exercise?
You are collecting personal data. The type of data what you have shown, it appears many of the things in European Union data protection, they will not be allowed unless they take a consent from the customer. Since India we do not have data protection law, are you taking the advantage of that?
No. So the way it works is that we don't take the customer's data. So the front end is,
for example, whether he has changed the cell phone or not, or how much time he has spent on which circle. These are all pretty private data.
if you apply for a loan, only then your data is stored.
No, I was asking, are you taking the permissions?
Yes. So once the first step is you give the permission that okay, I want to avail the loan, and then the question will be asked to you that will you be utilizing this data, and if you say yes, only then you will be scored.
Hi, regarding the regression model, right?
Yeah.
So it will always give the highest value. Correct me if I'm wrong. Yes.
Sorry, can't hear.
So in regression model, it will always predict the highest value on the graph. Correct. So is it advisable to use it or
Highest value is
I mean the greater value, not if you are predicting, right? So it's a straight line or the incremental thing. So according to me,
so we are building the logistic model. It will not be a straight line, it will be a sort of S-shaped curve. So it will give the probability of success. That is, success is whether the customer is creditworthy or not. So it will just give me a probability. If it is greater than the cutoff, I will take that as a yes.
So you mean you compare all the four models data and then you decide?
Yeah. So there is a bunch of model matrices that we use to compare. Something like the KS value, Gini value, or the ROC, AUC. There's a bunch of different technical information. I have not covered that in the PPT, but feel free to correct me. I will let you know how we compare different models. We also combine these models into one ensemble so that the accuracy of the model increases. So this is something which we have already deployed. Little bit about the outcomes, that whether this was good or not, how did it perform. So in the first phase, we have assessed the risk of customers based on telecom data of around 5 million subscribers. We have this is the pre-approved base. With this model, we can score and pre-approve the creditworthiness of around 50 to 70 million customers. Not all people will give a consent to the data. Not all people can be accessed. Data might be incomplete, or there might be some issues. So the target is to score around 50 to 70 million customers. In comparison to banks have around 5 to 10 million pre-approved customers. This is what the banks like HDFC or big banks have. So the objective here is to show that in the first part of the presentation I had mentioned that there is a huge bunch of population which are not being scored by any credit agencies. This is where the data science, machine learning, and AI help in solving that problem. You can have these customers who have difficulty availing loans. They can get approved by these models and get loans from any NBFC or any financial institutions. Also, in terms of performance, this model is performing much better than the credit bureau model by a factor of 5. So it's a huge thing for us. We don't have to rely on the credit bureau data anymore. This also eliminates the need for the customer to have previous history with lenders. Even if a customer is new to credit, if a customer doesn't have any history, you can still score them using the telecom data. So what is the next phase of evolution in this space? One is the telco database credit models. Another one is, which is actually getting a lot of popularity and also controversy, social media and online database credit models. There are companies who are looking at your social media data, whatever is available, and they are trying to score you, they are trying to assess your creditworthiness, they are trying to build your profile. Cambridge Analytica was one case. There are other companies also. We are not doing that currently. Your utility-based data is a very good source of information about you, about your lifestyle. If your things like electricity bill or water consumption or property bills, that's a very huge amount of information for building a profile of a customer. There is financial data, other alternate data. The holy grail for all this in this entire industry is one model to score them all. If you are able to build a model that can utilize all this information, or if say for example if the social media data is not available for one customer, but it can be scored by using other data, can this model predict the creditworthiness? This is what every company in this space is trying to build. The tools are available, the algorithms are available, but still there are few more gaps to be filled to actually achieve this particular model. Yeah.
If I'm a person who has no online footprint, so basically I cannot avail your service. Because you don't have any data that because you don't have any data by which you can predict anything about me if I have no online footprint.
Then we can't do that.
Sorry?
If you don't have any data, then we can't use that particular information. For example, this telco-based data is built for a specific set of customers, for say Airtel customers. If I don't have your data, you are a Jio customer or you are a Vodafone customer, I can't use this model to score you. We can score only if your data is available.
Only if the data is available. So basically, I'm trading my data to avail your service.
Yes, and that is specifically asked from you.
Okay.
If you apply for a loan, there is a checkbox that you will be using this data to build the secure score. It's the same as if you apply for a credit card. They also keep track of your data. They share that data with the bureau. If you are paying your credit card bills on time, that data is shared with the CIBIL and 3-4 other bureaus. So they also track your historical data and they share that with the banks. That's actually a regulatory requirement.
Okay, thank you.
So further applications in the whole, there are 3 billion unbanked and underserved people across the world. It's a 380 billion credit gap. This is what a lot of companies are trying to capture. If somebody is able to build this particular model or enhance this model to an extent, there is a huge opportunity of business in this particular space. So if any of you is interested in capturing a pie of this 380 billion market, feel free to build a model, solve this problem, build your own company. That's it, guys. Thanks for being here. Any questions?
You said your technology, you mentioned your technology was basically for banks or NBFCs. And what I understand is it's mainly for the retail base.
Yeah.
What if it's commercial banking? Are there technologies such as this
Yeah.
for commercial banking
Yes.
activities of
So
corporate banking?
this is a case-to-case basis model. We have built this specifically for consumer personal loans, consumer durable space for retail banking. There are companies in this, who actually work with commercial banks. There are companies who cater to the space of providing working capital loans to SMEs.
Could you name two at least?
In India, there is a company called Lending Card Loans. They are working in this space. They are not in the personal loan space.
On a global arena?
Global, I think Just Finance is one of them. Not very sure about Lendo does that, but I'm not very sure.
But these are principally fintech companies.
Yeah, all fintech companies. So fintech, the tech part of fintech is one is technology and one is data science, machine learning.
And that can be done for corporate companies as well, understanding their
The only
balance sheet.
difference is the data will be different. So you have to figure out how to build a model specific to that data. For example, this model which we had built was specific to telecom data. If we get social media data or if we get utility bills data, there will be a entirely different approach, entirely different models that will be built. Thanks everyone.
Thank you, Ashutosh. So over to Richard. He'll be taking up the session now.
Thank you very much. Stop me if at any point I mumble or go too quickly. But I was going to talk to you today about the idea of tap to human level intelligence and how close we are and what can get. But how close we are and what the stepping stones will be on becoming or producing an algorithm or a machine that is at human level intelligence. And then pretty clearly after that, superhuman. I said pretty sure. That better? Oh yes, it is. So who am I? My name is Richard Maddison. I'm from the UK originally, but I've been in Goa for about 15 years, close to now. I'm an engineer. I worked in TV special effects, making very fast hardware at the time when it all had to be done in the actual hardware structure rather than the software. But then fairly quickly moved into the oil sector to try and make more money. So I worked for a company called Schlumberger. They posted me to India, and that's how I originally arrived here in the 90s. So I was working on oil rigs, and it was pretty limiting. I did an MBA, got me out of that, and I went into finance and banking, making financial models, deterministic and probabilistic models, where they're effectively an expert system. So you're coding in the algorithms into the model, and that's how you do it. But there's been this big change, the machine learning change, which has meant that you set the brain up, you plow it with data, and it learns. And that's a dramatic change. And I think it's changing even more quickly. And I'm going to talk about what's happened in the last 5 years and how we would get there. I don't know how to advance the slide. Yes. So, what is intelligence? I think it's a difficult one to define, but you'd have a go at defining it first. And it's the ability to acquire knowledge, to use it, to learn patterns, to learn skills. And we see that machine learning is a way to do that. We see that we're getting tools that are, to some extent, pretty intelligent, but they're not quite there yet. So what you'd want to do is you'd want to develop a theory of intelligence, a mechanism of intelligence, to try and understand it better. And a good example of where we've done this before is learning to fly. So the next slide magically appeared. Yeah, cool. So we took inspiration from flying from birds, and feathery suits, flapping wings, it all seemed like a great idea. But it was pretty useless in effect until we discovered the theory of aerodynamics. Can I pop the next slide? So once we kind of discovered that, you get an aerofoil and you increase the distance over the top of it and pressure push the wing up, we start to be able to do things that the birds can't do. And we develop things that don't look anything like birds. It does look a lot like a bird, I'll give you that, but I think that can go at about Mach 7. It can go around the Earth in 6 hours. So we advanced what the birds could do when we got a theory of intelligence, a theory of aerodynamics. Can we do the same thing with the theory of intelligence? So next slide, please. The obvious way to go is to look at the most advanced algorithm we've got, which is trapped inside our brains. This algorithm was running on a couple of kilos of flesh, which is quite amazing. But what's it doing? And neural networks, the names it giveaways, clearly inspired by the brain. It is inspired by the brain. And what it's inspired by is this neural structure. Neurons that fire together and wire together. And if you're trying to learn something like putting food in your mouth, you slowly get it all over your face, and then slowly you train those neurons, they fire together, and you learn the pattern of putting food in your mouth, or you learn the pattern of a particular language, or how to translate, or how to play football, and it's a training process. And we've kind of got that. We've got this maths, the maths of backpropagation. It's been around for 20 years or so. But backprop, and if you're not familiar with it, it's incredibly simple maths. It's basically if you imagine two-dimensional shape of the surface, there's a function there that's got minimum. Backpropagation says, well, what's the local gradient of a particular place? We know how to go down the curve. We know how to go towards a minima. And if that minima is the difference between is that a picture of a cat and is it not a picture of a cat, slowly you'll close the gap with a neural network by closing it on the cost function with backpropagation. Now obviously the picture of a cat could only have 2 pixels there. So with that picture of a cat, 28 by 28, it's not very many, it's 780 dimensions. So you're trying to descend a mountain that's in a 780 dimensional space. But let's not explore it too far. The maths is still exactly the same as 2D. So that's the inspiration. But in the last 5 years, I think neural networks have completely gone out of this 10% fraction of machine learning and dominated everything. So there's a huge range of machine learning techniques. The problem with them is they're not particularly scalable. So they're genius. But when you start getting faster computers and when you start getting more data, neural networks win. In every case, I mean, correct me if I'm wrong, but all of the advances we've made in the last 5 years have been because of neural networks. Google swapped their translate from another system to recurrent neural networks in the last year. Siri, all the others. But the real point, the kickoff was 2012 when the ImageNet competition. The first neural net was used, AlexNet, I think, I can't remember, the error rate was about 26%, they dropped it down to 16. It was a massive change. And why? Because they were using neural networks. So that's the start. And that's when things came to the fore. On the next slide, I think what happened is this advance in computing power, this advance in data. And because we had that, we started thinking about neural networks differently. We started to develop new algorithms, and they were pretty basic tweaks, like the relo activation function. I mean, who would have thought that something quite so simple would dramatically change the speed at which models settle down? This is a rectified linear unit. It's a straight line with a bend in it. Everything below zero goes to zero. So little tweaks to the algorithms are making massive advances, as we would do when we get a theory of aerodynamics, we start improving the system. So we've got these voice recognition systems outstanding. Google Translate just changed to self-driving cars. I mean, to have an evolved algorithm with a fleshy kind of substrate driving the car is lunacy. They're killing everybody. It's the most dangerous system in the world, the Indian road system, to have humans driving it. So if we can get them out, get the AIs driving, we'll see the death rate go down by 1 million. My guess. You know, this is what we can do with pattern recognition systems that aren't reliant on human frailties. Image recognition. I spoke to my phone and asked for pictures of something. It scoured my pictures. I didn't realize Google had done this, but they're looking at all of my pictures and categorizing them. So the ability to identify objects in pictures has just outstripped human ability for speed, obviously. Maybe not accuracy yet. IBM Watson, that's quite impressive. AlphaGo. I mean, all of these things were measures of artificial human intelligence. And they were the benchmark at which we would say we've achieved it. But every time they were reached, the benchmark got a bit further away. So artificial general intelligence means anything a human can't do. That's the definition as far as I can see. Because all of those benchmarks are changing. One of the most exciting ones, I think, is AlphaGo. And on the next slide, I think this happened about 10 years too early. I don't know about you, but well, throughout my life, all scientific advances have been 10 or 20 or 30 years too late. Nuclear fusion has been 30 years away, or 60 years. It was 30 years away when my father heard about it 60 years ago. But this victory in Go came 10 years early. Now, Go is a game, if you don't know it, it's the longest continuously played game on the planet. We've been playing it for 3,000 years. We've put vast amounts of effort into this game. In China and Korea, they've got schools where they've got the brightest kids and they train. So 3,000 years, and this guy, Lee Sedol, is a sort of Federer of Go. He's a genius. He's dominated for 10 years. He's unstoppable. And he played a game against Demis Hassabis's team, DeepMind. It's a London-based bought by Google. And they used 2 neural nets in a clever way. One neural net trained on lots and lots and lots of games. The other one, a value net, saying, is it likely to win? And then some Monte Carlo research. Neural nets to kind of explore the future space, and they beat him. They beat him 4 games to 1. That's the last human ever to beat a computer at Go. And then a few months later, they developed AlphaGo Zero, but they didn't need the humans. It just played itself. They introduced recursive neural nets as well, slight changes. And now, if he's a 9-dan player, this is the 12-dan player. We don't understand how it plays. When it played itself, I advise you to watch the Netflix video to see this documentary. But they set this machine off, and for a couple of hours it plays like an imbecile. Within the rules, like an imbecile. Then it starts to play like a greedy human. Then it discovers the Giuseppe. The Giuseppe are the edge moves. So these are moves that humans have learned over 3,000 years, like closing moves in chess. Well documented, simple, but only a few of them, and they're known by the humans. So it learned them all within the next 10 minutes. Then it learned all the rest we hadn't found in 3,000 years. And then it went on. And now it's unstoppable. The chance of Lee Sedol beating AlphaGo Zero is about 1 in 100,000. It's almost impossible. If luck is on his side, he might scrape it. So that happened. Happened 10 years early. Okay, happened next. So I was going to talk a little bit about the baby test, the MNIST digits, which if you're involved in data science. This is the hello world, you know, you put in computer print. And this is, the idea is that a human, well not human, but several humans with this French bloke, Yann LeCun, wrote 60,000 digits, 0 to 9, and they know what they were writing, so we've categorized it. We know what this is a supervised data set. It says it's a 6, the human tried to write a 6. And in some cases it's a bit dodgy, and if the next slide, there's some particularly dodgy ones on the next slide. And they're getting up to this theoretical Bayes limit. And that's the limit at which you can distinguish between cases. They have enough information for you to allow a distinguishing between cases. It's not possible to categorize these more than the Bayes limit. Humans have always been the measure of where it is, because we're very good at spotting these. And I think we're about 99% of this data set. But the algorithms, and particularly the convolutional neural nets, are getting 99.8, so 0.21% error. Quite impressive for a neural net. Now, a neural net, I don't know if you're familiar with it, but what I was hoping to do is show you a neural net. And it's an exciting view of a neural net, because it's in Excel. Now, clearly that's not the normal thing to do. I've never seen one before. I built this one. I don't think anybody's built a neural net in Excel. And what I'm trying to show you by that is how simple it is, how simple the maths is. So next slide, please, if you could. But I'm going to put this on a spreadsheet. I'll talk you through it as a PowerPoint slide first. That's 2. That's the first layer. That's the brain of the first layer, a convolutional layer. It's got 4 kernels, 5 by 5, and these swing across that image and they look for features. The next layer, which is 8, that's swinging across the other channels. It's got 4 different views of this 2 channel that's stored here. And then there's 2 fully connected layers. So that's the brain in here, in here, in here, and in here. So this is the top level. The sheet you were looking at before is that one there. Sheet 1, but there's 10, because it's a 10 case model. I'll show you what it looks like. That's sheet 1, sheet 2, but only sheet 1 has got a brain. And now I'm going to run it. It's completely ignorant. And now it's learning. And the error rate is 15%. It's good as flipping a dice. You're going to get it right 1 in 10 times. Because there's 10 digits. But it's starting to learn now. It's at 30%. I don't know how long it took you to learn these digits, but it might be learning quicker. And it's devouring these numbers, and slowly you're seeing all of this go green, where it's presented with a number, and then what does the model think it is? It's learning these canonical letters, 0 to 9. This is a confusion matrix. I love the name. The computer gets or presents the model with digits 0 to 9 here, and then the spreadsheet's guessing what it is. So if it gets it right, you start to get this very hard line of error. And so when I built this about a month ago. It didn't take long, we built lots of models. We built Excel models. I kept wiring it wrong, it was late at night, and over a week it was a disaster, but I just kept learning. It didn't matter how much I messed it up. In fact, only today I found out that 2/3 of its structure was broken. It was still learning up to the 98.4%. So that's how robust a neural network is. And when I've been taking neural networks off Keras to run it against, I'm finding that they're completely bust. You know, they're twisted and distorted because the channels first, or you know, that we're looking at the wrong shape of neural network, but it still learns up to 97, 98%. You can store that much information, that ability to recognize patterns. Now, I'd like to look at it all day, but I'm sure you're not such a spreadsheet junkie. So that's got pretty high. It's 300 iterations. I'll escape, and then we'll get a curve out of it. That's the precision rate going up. This is cumulative. So it's actually probably got to about 90%. This is the loss rate, the function that we're trying to close. So yeah, it's amazing how these things work. But they don't work like us. Can I try the next one? Yeah, they don't work like us at all. If you do a neural network to recognize faces, in particular this, who's a head data science at Google, head of data science at Google, if you ask it to replicate what it thinks his face is, it comes up with something like that. You can't really tell that it's not a face. That's what it thinks a face is. And it thinks it's a face because we've had to apply this neural network with hundreds of thousands of pictures. I know you can't hear me when I do that. But it's not the way we learn. It's but it's the way a convolutional neural net learns. So for instance, with these figures, if you want to learn that that's a guy with a gun or a horse or whatever, you need to show it from every angle. And that's not really how we learn. We would get an understanding of the shape, and when it's rotated, when it changes, we'd still be able to recognize what it is. So, okay, it's not how we learn. But how do we learn? Do we understand how the brain works? And on the next slide, there's various little glitches in the way our brain works. I'm sure you've heard the Yanni Laurel thing. This is once your brain has decided the framework for this phrase, you can't escape it. So you're trapped by imposing a framework on what you hear. Likewise with this is a two-piece jigsaw puzzle. I wanted to have one made. But if you give it to MIT professors or very clever architects, they can't do it. In fact, they'll give you a theorem of how it's impossible to make a tetrahedron, a four-sided pyramid, on the bottom four-sided pyramid. They'll tell you it's impossible. It's impossible because they're imposing this triangular coordinate frame on it. And this is going to join as a rectangle now. Unfortunately, I don't have the model, I can't show you it. But let's move to that lesson. You instantly know what that is. It's an R, it's an upside down R. It's not. It's an R flipped back to front. But because it's out of sync, you can't recognize that it's not an R. You can't see the mirror indication unless you slowly tick it round and bring it upright. If this is a diamond, as you probably think it is, you can't really judge the angles here. You can't tell it's a right angle. But as soon as you see it as a square, your ability to say the angles are on that corner or right angle is much clearer because you imposed a coordinate frame on it. So, oh dear. So this bloke, Geoffrey Hinton, has been working for 30 years on a different model of a neural network, a capsule net. He released the paper last year in November, so it's not even a year old. And it's quite staggering some of the improvements it can offer. And I'll talk a bit about those. I was going to attempt to explain how a capsule net works. I'm hoping not to get too many detailed questions because my maths will fail, but I see people nodding who know what they are, so they can answer. So Geoff Hinton said, I think the brain works a bit like the way we make computer graphics, but backwards. So what does that mean? It's inverse graphics is the way he describes it. So if you think of the way in a computer game or when you're rendering an image from a computer, you have an abstract representation of triangles, squares, particular shapes. You've got a relationship between them and you can make the figure that is composed of those shapes do things. You can twist it around, but all of these independent bits are moving with it. So an architect constructs a model of a house, it's made of pillars and columns. They're all moving together. There's a hierarchical representation of how they fit together. And what he's saying is that neural nets, or the capsule net in particular, works like inverse graphics. So it's trying to find the component parts of the end image. In this case, a sailboat. It's composed of these two elements. So we're looking at the elements and we're trying to use those elements to predict the next set of capsules. I've shamelessly taken these slides from other people. Okay, so capsule net is in the lower level, rectangle, triangle, it's composing a higher view which makes a house. And actually going to go one slide further. What the capsule nets are doing, and the way to think about it, is every capsule layer is trying to predict what's in the layer above. It's trying to say, does my component part fit within that layer above? And if it does, you've got a prediction that works. And that's a kind of understanding of entities, these squares that build up to larger entities. And this is a look at about, you would say, is that 5 by 5? 5 by 5 capsules, 25. And there's a black one and a triangular one. Each of those entities are a capsule. So we've got a capsule looking for a triangle or a capsule looking for a rectangle. Now, when we train a capsule net, they don't make these shapes, they find their own shapes through backpropagation. So this is a kind of potential perfect case where it was a triangle and a rectangle. And a capsule net encodes that information in two components. It encodes it in, is it probable? Does this shape exist on the final image? And what's the pose of the shape? Is it rotated, or is it what shape it is? So in this case, we've got a rectangle and a triangle, very large arrows, that represents the probability of them being there, and they're pointing in a particular way. If the relationship of those is what the final part is, then you're going to get an agreement. I'm not going to discuss this very well. But the next slide, perhaps. Down a bit, other way. Oh yes, no, this is good. Okay. So the pose of these capsules, the pose of these small entities, the instantiation parameters, where it's rotated, is it forward, is it big, is it small, is it shaded, they have got a relationship to the final object. And if we look at two of the parameters, this is rotation, this is the final shape and how much is rotated, this is the scale of it. If you imagine that these dots are capsules, two of these dots, one of them is a triangle, one of them is a rectangle. Now, if the rotation of the upper object, the ship, is represented, the triangle matches it, and it also does for the rectangle, then they're agreeing. They're saying that the way these two objects are orientated match with the higher level capsule. So they're making a prediction of, do these both form part of the ship? Now, this is in 2D space, but it would probably be in 20, 30, 40D space. And if you get a coincidence in higher dimensional space, it's really, really unlikely. If you've got 6-dimensional space and everything's falling in a 10% band, it's a 1 in a million chance. So the probability of these rectangles and triangles predicting this final shape, if there are only 6 dimensions, will be very, very high. So you can find that if the capsules are clustered together, the lower level capsules are predicting an upper level capsule, a thing, an entity that we're trying to discover. So that was just the magic of capsule nets, is this routing by agreement, where the capsules are trying to vote for what the next layer is. I'm going to move on quickly. Next slide, please. And the next slide. So, why doesn't it confuse things like this? We've got a house and a boat. But you could say there's an upside-down house. Well, you get a lot of agreement for the boat. You've got 2 things agreeing for a boat that's tilted like that. You've got 2 things agreeing for a house, but you've only got one. The other 2 aren't. So the voting of the capsule net would devour that and show you that there are 2 things in existence. So it's very good at separating overlapping images. In fact, even with this kind of Mickey Mouse version that came out in 2017, it wipes the floor with all the best convolutional neural networks, things that are laying on top of each other so you can see individual things. This is the layout of the capsule net in Hinton's paper. It's got 2 bits. That's the capsule net up to there. I would recommend looking at the paper, but that will predict categories of things. Letters, 1 to 2, or pictures of cats. This bit's a decoder. It allows you to take the vectors that come out of the capsule net and from those vectors regenerate the images. But this has an interesting effect. It means that you can run factor analysis on this, get out the core components of the letters. And in the case of the NMIST dataset, this dataset, I needed 60,000 labeled images to train it. With a capsule net, you need 25 questions. 25. That's more like a baby. That's more like the way we learn. Very limited amount of supervised training information. This is how the 2 moves when you stretch it. 25 inputs, 25 bits of supervision to learn the data set up to state-of-the-art training. So if we can start learning from unsupervised learning with very few questions, a limited amount of supervised learning, and we can get it in a structure that can interact with the outside world, we've got a baby that learns like a human, but at the speed of light. So, what does that mean? That means that potentially we're very close to artificial general intelligence, and therefore superintelligence a few days afterwards. Next slide. This is just a little bit about it, but I'll not go on unless there are questions at the end. And next slide. Oh, and this is about the vector activations at the end of the capsule net. I mean, you can mess around with what they're doing to particular categories. Now, these are just happen to be things like the scale and thickness. If you change some of those instantiation parameters, think of these as the location, rotation, but there are other things. You can see how they behave. So you can understand how the model is encoding the capsule and the shapes. It's incredibly intuitive. Next one, please. Pros and cons. I think I said these. So it's already got state-of-the-art on these letters. Requires very little training. It captures the shape and the orientation and the hierarchy of components of a larger shape in the model. Routing diagram is the clever bit. It's by Jeff Hinton, really. I think that's the thing. You know, everything else he's done is really, really impressive. I was doing a training course on this, and he had, on his training course, he'd said, well, you could do this. I think it was Dropout. He just casually threw it away in the training lesson. This is now the primary way that we train networks. But this sort of development is happening all the time. So, I mean, generative adversarial networks, GANs. Ian Goodfellow, he had an argument at the pub, and he went home that night. And before midnight, he'd coded the first generative adversarial network 2 or 3 years ago. So the field is moving so quickly, and so many people are sharing these ideas, that I think we're incredibly close to artificial general intelligence.
Do we have any questions?
So you were nodding all the hard maths, so I'm a bit worried now.
Not at all. I just wanted to know, how do you use it in your business?
Well, the bulk of my work is still in making models for oil companies or banks, and they're still primarily deterministic, not neural networks. We're engaging with Viacom to build an algorithm to watch soaps. So at the moment we're looking at ways to look at Big Boss and correlate that with the viewership figures and with the social media tweets to give script recommendations. So this is just a way of looking at large amounts of data. With Numadic, I do work with Numadic. There's all sorts of interesting things that we're looking at. Most of which I'm not allowed to talk about. Lucas told me. But we are looking heavily at driver and vehicle scoring with this by gathering information around it. And it's always going to be neural nets. I would see no reason to go down any of the other paths. But thank you.
Thank you, Richard. So over to Anubhab and Utkarsh. They are our third and fourth speaker. They are from HandyTrain and yeah, over to them.
Alright, good evening everyone. Am I audible at the back? Good. So, before we begin, first of all, I am Utkarsh, this is Anubhab. We are respectively heads of product and technology at HandyTrain. So before we begin, I wanted a quick show of hands. How many of you are currently working with machine learning or data science as of this moment? No. And how many of you intend to work on anything related over the next year at least? A bunch of hands. Good. So we hope this talk will be useful to you because what we intended to present was essentially a set of very practical hands-on advice on how machine learning can actually be implemented. When you read about machine learning and AI on the internet, you'll find a lot of very theoretical blogs which are very hard to follow, also very intimidating. At the same time, you can sometimes come across very advanced libraries which are also very difficult to implement. But at the root of it, it tends to be extremely simple, especially if you are an implementation person. So we'll relay our story of what we did, how we learned from our mistakes, and how we have implemented it. The core idea being that if you're an engineer, if you can code, you can definitely do machine learning.
And the point of note here is that everything we talk about is from two of our experiences. In case one, we were classifying emails into tasks, notes, and so on. And the current one, which is essentially parsing through your open presentations, Word documents, and so on, and trying to generate consumable content. So bite-sized content out of it. Basically, we have to figure out the visual hierarchy of a document. This is the heading, this is the body, this is the crux of the content, and how it's going to place in a mobile phone. That's what we are working on at HandyTrain, right? So everything we talk about is basically based on these two experiences.
Right. So this is what we did earlier. When we first implemented machine learning in our previous startup, we did two things. Okay, both of them were wrong. The first one was we tried to sit down and understand the mathematics of machine learning. We tried to understand how the algorithms actually work. Okay, that was one. We understood that to a good extent. Then we went on and we hired an expert. This person used to teach me at IIT very earlier. Then he went to become a researcher at Harvard and later on at UCB. He was planning to move to India. He was a core machine learning expert and AI expert from the academics. Harvard, University of California, Berkeley, it doesn't get better than this. And we hired him. And we said that now that we have a real, renowned, well-published machine learning expert, we are home. Okay. In 6 months, we had zero. Okay. So we understood that there was definitely something that we were doing wrong. There was nothing wrong with us, nothing wrong with the expert. He was genuinely an expert. We were genuinely working hard, but we had no. Okay. The reason was we had done some very fundamental mistakes. Okay. So the topic is machine learning as a hack. How do you get it moving? So this is the fundamental mistake we did. Now we understand this. There are two aspects of machine learning. Okay. One aspect is the algorithms, which is theoretical and academics driven. Right? You need to understand a lot of mathematics to be able to understand this. You need to go to the details of how a neural network works, how a neuron works, right? How to architect a network and so on. How essentially, let us say, SVM works and so on. Right? Other part of it is the implementation, where you basically need to know how to pick an algorithm, how to take data and apply that algorithm to that data set. It's as simple as that, right? If you hire someone who is an academic, he'll do academics, right? He will not be the implementation person. He's used to building everything from scratch, right? So they will not be able to do, and they should not do, what engineers do. On the other hand, for most of our practical purposes, we don't need to understand or create new algorithms. We just need to look at what is already there, pick up some libraries, and know how to use them.
Right. Another mistake that we did, we started off saying that we'll solve something with machine learning, which is disaster. Because then you're solving the machine learning problem, you're not solving a real life problem. If you're trying to communicate with, let's say, create a communication suite which talks to thousands and tens of thousands of your users, you don't need machine learning for that. You need a sophisticated rule engine at best. Come to machine learning only when you have to, when your possibilities are becoming endless, you cannot tackle. And the real test that we are doing now is, your font sizes of, the way I create a presentation. I use large but non-bold font as the heading. That's how people do it. I mean, you will have a bold font, you will have a different colored font to differentiate. That's where your rule engines will fail, because that's where you cannot tackle the context anymore through specific tools. And that's why you identify that this problem could be trained and tested and implemented through a machine learning problem. Second problem was that in our previous implementation of machine learning, it's basically we have both of us sat together and our inboxes, we put those into some kind of labeling and this. But that data is biased, that's no data, that's absolutely nothing. And now when you do that, basically the outcome is the moment you put it in production, you will see that it's all over the place. Blank emails started to get classified as, let's say, tasks. And it doesn't make sense. So first, when you start thinking of it, think where do you get the data? You have enough data to start approaching the problem.
Right. So the concept here is that you should not do algorithms first. You should think of data first. Algorithms can come later. As geeks, we got too excited. We picked up different algorithms. We wanted to understand them. Everything looked so sexy. We were like, we're going to do this and this and this, right? And we ended up classifying empty emails as tasks. That was what. So this is a series of steps that we believe that you should apply. The first one obviously was choose when to apply machine learning. Don't think of machine learning as an end unto itself. Only apply it where a rule-based system. A rule-based system would be an infinite if-else statement. Right? When it is huge, when you cannot apply it, that's when machine learning is important. The first step is human labeling of data. Right. So our mistake was we started with too small a data set. Okay? We did not know how to generate a substantial data set to train it, right? And if you have 4 people sitting in the room trying to do something with their data and understand how to classify it, there will be biases of humans. As humans, we are prone to biases, right? The hack here is you can use a crowdsourcing platform, right? So this is the step where most of the early stage machine learning implementations fail, because machine learning is 80% data and only 20% algorithms. Right? If you do not have data, you can't do anything. If you have raw data but not labeled, you'll fail. Right? So first thing is you have to gather some data from somewhere and get it labeled by human beings from a crowdsourcing platform. If you don't go to a crowdsourcing platform, if you can get labeled data from somewhere, so be it. That's great.
A quick point of note over here is that be very careful about what you are sharing in the crowdsourcing platforms again. And there are ways to ensure that you don't share personal information, you don't share someone's private data. We were working with emails, so we started with emails of all of our, the common team. Then we moved on to emails of friends, where by explicit content, by removing the names, the dates, and so on, and thereby generating certain data, certain valid data. But that's a problem.
That's a fairly valid point. Second one, you need to understand patterns of the data. So before you get into a complex algorithm, get in there, you need to understand the patterns of that data on your own. Okay. What happens is you may have preconceived notions. So when you are solving a machine learning problem, you have a hypothesis in your head. You decide that let's say I want to classify an email as a primary or a secondary, something that Gmail does. Correct? You start with a hypothesis. You say that if this email is from an important person, it should be primary. If it is not from an important person, it should not be primary. Very simple. Correct? Then you will ask yourself, what constitutes an important person? Correct? So that is where you start to get into data and details of machine learning. But before that, you need to understand the patterns on your own.
So talking about the preconceived notions, the current problem that we are facing is that when we started the first implementation of the document parser, we started to consider even the presence or absence of words to mark it as a heading and body. But when you are trying to, so our content, the content which is parsed in HandyTrain is varied across industries, across languages. There would be a lot of so fitting those blocks, fitting those notions of even using, let's say, the presence or absence of certain words and classifying it as title is a preconceived notion which failed miserably. Second problem was we started, when we looked at the data, we started saying that we'll have this, let's say, 30 different parameters or 40 different parameters to start working on. Be it heading, be it bold, italics, font family, colors, frequency of the particular type of words that are used. But again, when we started it, when we first started running the algorithm, the accuracy was extremely bad. So that was the mistake. How we worked on it was we just reduced the set. We started with the most obvious ones, which is font size, which is bold or italics, presence of bold or italics. and interesting. Here was the frequent in an entire presentation or an entire set of data that we have. What percentage of this kind of style constitutes to your title and the body, and so on. So when we reduce the data set, suddenly we started seeing spikes in the accuracy, and then we started increasing and introducing patterns and features too. Right?
So the hack here is to visualize the data. So any of the machine learning experts and data experts, they know they do this all the time. Any tool that you will use, any software that you use, will almost definitely have a visualization tool. When you start off, you tend to improve it. Don't do that. This is an example. Okay. This is what we got when we tried to visualize the data. As Anubhab was mentioning, we want to classify it as head or body. Fairly simple problem. This is what we got. Even a human being can't tell how to draw a line that will separate all the red dots from the green dots. It's not possible. A line or or any curve for that matter, right?
So red dots over here essentially represent your titles, and the green sector represent the body in one particular
So at this stage, we understood that there's something wrong with it, right? So sending this data to any algorithm would give us garbage. It would not give us a real output. So we started to analyze this further. We tried to think what's wrong with this, right? And then we went further. We'll show you in a moment what we did and where we reached and how did we proceed. Okay. Third step is picking an algorithm. Right? Once you have analyzed this data and once you have understood what is the end goal that you want, you can pick up. This is the stage when you start thinking, what algorithms should I apply? Application of algorithms will depend upon a lot of factors, right? Depends upon how much data you have, what is the kind of problem you're trying to solve. There are a lot of literature on how to pick an algorithm. It will also be dependent upon your own limitations, your own team, whether you have enough data to do an unsupervised learning or whether you should stick with supervised, what kind of a problem it is, and so on. We'll not get into too many details of this. There is no shortcut.
Work for us is essentially passing the same data set with multiple different algorithms. But first, reading up about what is the closest implementation that you have. So you're trying, but there are classifiers available. There are people who are already classifying. There's literature available in the market. Pick it up, test it with your data, and show you how that data is. Is it visible?
Now it is not. Yeah.
What you see over here on the top, this block, these are your features that we are working with at this point of time.
So by features, we mean different parameters that will help us classify a particular line into technology.
Right. And this is the label which is generated by some human. We have a lot of data coming in from all our clients, and which is a lot of learning content which is available already in the market as presentation, open content available. So some of us have already sat down and labeled all of them based on this. Yeah. So now pass this data through different algorithms, and you start to see patterns emerging. Something will give you better accuracy, something will not give you better accuracy. Test it with all of this data, and then you can probably start to see that this is the kind of algorithm which works for us. Then build on it. Build on fine tuning it and get the best out of it.
So we are oversimplifying it a bit here because the entire detail is beyond the scope of our talk. But once you pick an algorithm, obviously you want to optimize it further. You want to change all the different parameters that you use and figure out what works and what isn't. So it's a fairly long-winded process. It's not you won't get to a solution overnight. But there's no shortcut with this. Now, step 5 is pre-processing. This is what I was talking about earlier. The same diagram that you saw had data which was not processed. It was raw, right? So in pre-processing, you apply a lot of mathematical statistical tools. You pre-process the data by converting them to web, by first cleaning up the data, say normalizing it, vectorizing it, and so on. There's a series of steps that you follow, and you arrive at a data set that is usually zeros and ones or within that scale. The entire data set is in the same scale, right? It is not dominated because of, for instance, if I was mapping the heights of all the people in this room, and to map that, we also brought in one person who was 7.5 foot tall, right? So the percentage difference between somebody who's, between me and Anubhab would be very small, correct? That won't be like this, correct? So you don't want extreme outliers, unless outliers are a part of your data set, right? But if they're not, then you need to clean this up. That's just an example, but that's a subjective call. You need to decide whether you want to do that or not, right? But once you think about process, what you see before becomes what you see after. At this stage, an engineer looking at it will start to gather an understanding of how he might go about drawing a line which will clearly classify the two cases, right? It's important to understand that there will always be some outliers. Like you can see, there are some red dots here and here, right? There will be some that tells you that the accuracy won't be 100%. But that's fine, as long as you can draw simple line somewhere else which can classify it, well and good. That's your starting point. Step 6, test, rinse, and repeat step 3. So at this stage, you run your training, you get the accuracy, you find what is the accuracy of this, you change all the parameters one after the other, and you try and find out what works. Fortunately, today there are some tools available that allow you to automate a bunch of this process. We'll show you something very fair.
So we talked about trying out different algorithms, right? Now, it's not a very lot of mumbo jumbo over there, at least not for us for implementing. A lot of hard work has already been done by the smart people in the world. So essentially, I think it boils down a lot of time to this code scaler. And it's very well established framework, library. And I think all the algorithms which you need to start building your first machine learning implementation. And you will solve a lot of problems. And then with the same model, same everything, essentially you go down here. You can try out different algorithms and see how they perform. So here I'm trying KNN classifier. It's one of the simplest implementations of classification problem. And we talked about the rinse and repeat part, right? So in every algorithm will have its own nuances which you need to tweak. In KNN there's a K value which you need to tweak. So you want to run this? Yeah, so see essentially what we are doing is I'm running it from a range of 1 to 25 to figure out the maximum accuracy, right? What you get running this. So at K value of 5, we have the maximum accuracy. Or at this point of time in our implementation, I think we are good to go. This is what we are sticking with, and this is what we are going on.
So you can look at the blue line here. This is the testing accuracy. Don't worry about the training one, right? You see how, as the K value keeps changing, the accuracy keeps changing as well. We get a peak over here, right? This is not the final thing. So what happens is the more you change your data, the more you change any other parameters, you will start to get very different types of results, right? But this is one way of doing it. You can plot it, you can see what works, and then fix that parameter and start to change something.
So I'll show you with that the same in action our own product.
So this is what we have been working on right now. As Anubhab mentioned earlier, you upload a PowerPoint presentation. It reads a PowerPoint presentation like a human being and tries to decide what text is title, what text is not. Right? It's fairly simple for humans to understand, but not so easy for computers because things can change. Right? So he's uploaded a document here.
This is essentially the presentation that we are converting into a bite-sized content as we call it. This is the result. This is the output.
So let's take the first slide here and second slide and let's compare it to the slides.
This is the output. So the heading is here, the body is here, the bullets
context here. So,
It's a fairly simple model, nothing very fancy. But even for this to work, there's a lot of data-related work that you need to do. Picking an algorithm is fairly simple in this case. We could have picked up SVM, we could have picked up KNF, we could have picked up even CNN for that matter, or a neural network of any other kind. But we didn't want to overcomplicate the problem. We didn't want to overcomplicate the solution. We wanted something that works 99% of the time and is quick to implement and push in production. Now, in production, there are a bunch of things that are super important. The entire scope of machine learning as a field really started with Google search, when data mining came into lives of all of us. Google search was very simple in the sense that if it got the search result wrong, it wasn't going to kill anyone. Right? It was fairly simple. If it showed me something on the first page that was not relevant for me, that's fine, not a problem. Right? But every single time I selected one of those suggested options, Google recorded it and stored that information. They recorded the data for a huge number of years, and then finally they made Google search use the best. Right? So now the Google search that we see, the results that I'll see would be very different from the results that any of you will see, right? Depending upon who we are and what our past searches do. That's one of the key points here. We had done a mistake earlier at one point in time of not capturing every single user interaction with our model. But that's something that is strongly recommended against. You should always capture every single interaction and use that later to improve your model. Okay. At the same time, if you can build an intermediate model wherein you're just recommending something, people are selecting something, and we're using that to very rapidly iterate on the model and improve it, that's even better. So that was the final learning that we had. Take that again. Is there any questions?
Example what we showed, the data is static. But in the real world, data has got another parameter called velocity. That how fast you are getting the data, and you have a dynamic model. So you know, the time is also a part of your function.
Right. So I'll repeat the question for the audience. The question is that there is a velocity of data. There is a lot of data that can keep coming in, right? And how do you factor that?
Typically, what you generate are pretty training, right? Real life, when you actually process the data, you are sorry. In the real life, when you are actually processing the data, you'll not be looking at it at that point of time. During training, you will be generating these visualizations for your own understanding, right? So, you can keep it as a parameter, but it's not necessary. Again, depending on what you are looking at, if you are trying to find out that.
So there's two things. One is this, essentially that when you're looking at the data, it's a snapshot data. Okay? So you're taking a snapshot and taking it. There's a field called online learning where as you interact with the data, pretty much live, the data is being recorded and approaching. That's extremely processor memory intensive, usually companies over at regular intervals keep taking the snapshot of data. Does that answer the question?
we have a problem that you're solving, right? Instead of getting the content being created, just take existing content, parse it, put it in convert it to Python.
That's right.
You use ML for understanding what that is.
Absolutely.
So, scientific use.
It is. Yes. So what happens is that HandyTrain as a company we help larger companies create distributed networks. You do very good networks.
Yeah.
So what happens is that a lot of our clients tend to have a huge amount of PowerPoint presentations already with it. And for them to convert these presentations manually into bite-sized content is very painful. We have a content, we can upload it as a handout and everything. But that won't be bite-sized, that will still be a presentation. So we needed a solution. Which would take this existing content and convert it into real bite-sized learning in a format that is very native to the HandyTrain platform, right? And it's why native is important is because we knew from our previous research that content is much more engaging than a raw PowerPoint presentation. So
Especially when you are looking at it on a mobile device, it specializes on mobile training. The mobile device is very important to have it in the digital school.
And so it's only for using existing content and convert.
That's one part.
Absolutely. It's only for existing content. You don't create content. Content creation is a separate engine. It's not part of this machine learning.
converting last one is converting power. You have this alternative like using PayU, where you can take the data and straight away convert it to PayU. Because people have reservation about power.
No, I understand that. So that's most of the conversion problem, right? There are tools in the market which can convert latex to PDF and vice versa, right? We are not into that. We are essentially allowing you to convert something that's PowerPoint designed for desktop automatically into some bite size which is designed for mobile. That's the problem we're trying to solve.
So the final output that you see is just the data at that time. The visual way can change and will change over time, but the data remains the same.
Okay, thank you very much.
Thank you, Utkarsh and Anubhab. So before we call upon Ashish, I would like to go around and would you guys, you can hand us over the puzzle sheets finally. We'll take it from you and yeah, and then Ashish will come up for his session.
Hello. Am I audible?
Yeah.
Okay. I'm Ashish, TempoGO in Prototyze. Topic today for me, challenges of IoT, tools, techniques, and I'll try to give you a reference architecture in a presentation. So disclaimer here, all opinions are mine and nothing to do with TempoGO. Okay, let's begin. This is my agenda. What is IoT? How does it work? IoT values and benefits, challenges, protocols and standards. I'll talk about data protocols, database and performance, and building a private IoT platform. What is IoT? Anyone? Okay, I'll read the wiki definition. The IoT is Internet of Things, is the network of physical devices, vehicles, home appliances and other items embedded with electronics, software, sensors, actuators and connectivity which enables these things to connect and exchange data, creating opportunities for direct integration with physical world into computer-based systems, resulting in efficiency improvements, economic benefits and reduced human exertions. Very big definition. The simple definition is down there. The Internet of the Things is actually pretty simple concept. It means taking all things in the world and connecting them to the Internet. There are three broad categories. Objects that collect information and then send it. They are like GPS devices, sensors, etc. Second one is objects that receive information and then act on it. They are like printers connected to internet, immobilizers in vehicles, so on and so forth. And then there are objects that do both, drones and driverless cars. How does it work? Any IoT consists of three components: hardware, their devices and sensors; network, from where the data is sent to the servers; and the software, where data acquisition software and the data processing software. Collecting data isn't one size fit for all. IoT has two dimensions: time and data. Time is the frequency of data collection, and data is quantum of collected data in each pass. I'll give you two examples here. In case of cars, if you are collecting data for engine, then you need data every second or even 10 seconds. However, if one is collecting data on home surveillance system, then the data is required only when there is an intrusion. So the time and frequency of data also determines the bandwidth and the processing power required at the device. So it's very important to choose what should be the frequency of data collection and what is the quantum of data to be collected. There are four common patterns in IoT. I'll walk you through one by one. The first most common pattern is M2M pattern, which is the oldest pattern where people connect through VPN to enterprise IT. Here this pattern is not scalable because enterprise IT itself is not scalable. So it is not built for scaling, but it is basically used for people in that particular organization to connect to their systems. So next one is smart remote controls. It's a remote control like this, which acts with one device and some Android or iOS apps who also can operate as remote control, but essentially it's a device and a remote control, so it's only one way. So only one user can use one application and one tenant per device. Next pattern is IoT gateway. Central gateway gathers local protocols, connects to cloud, and then scales as needed. Works with multiple users, tenants, applications, and ability to connect to thousands of users. Primarily, when we begin, we start using this kind of architecture where the devices are on one side of the cloud, they connected to the server through cloud infrastructure. So one can scale device with the and one can scale applications and users. This has a problem. Take an example where you have multiple devices and multiple applications. So each one will have a separate gateway. Example, if you have a coffee making machine and an AC and a car on a IoT and they are on a gateway, everything has to be programmed. So I will reach home at 6 o'clock, so AC should be started at 5:45 and coffee machine should start at say 5:30. But if I get delayed, then what happens? I mean, it doesn't work. If you come early, it doesn't work. So then there was another solution. Iot Platform. It was built on a common platform with standards and semantic interface to the same platform. This can invite developers to build applications to serve the market. So you extend the previous example and imagine the same thing was on the platform. Then intelligently it detects that you are 30 minutes away from the distance, or your distance is 30 minutes or maybe 15 minutes. You start AC, 10 minutes you start coffee machine and you're there. What are the values and benefits? So increase in business opportunities. The typical example is us. We at TempoGO use this technology and provide value to the users. Enhanced asset utilization, efficient processes, improve safety and security, increase productivity, and for that, saving cost. So this is taken from McKinsey report. This is US data in 2017. According to McKinsey, the potential is 3.9 trillion to 11.1 trillion in year 2025. This is the bifurcation. Home is 200 billion to 350 billion. Offices 70 billion to 150 billion. Factories are 1.2 trillion to 3.7 trillion. Retail 410 billion to 1.2 trillion. Health and fitness 170 billion to 1.5 trillion. Logistics and navigation is going to be 560 billion to 860 billion. Public health and transportation is 930 billion to 1.7 trillion. Vehicles to 210 billion to 740 billion. So though it is US data, the Indian economy, the way it is growing, even if it is 1/10, it's substantial. Now there are challenges. The first challenge is data. IoT data is fairly simple. It's timestamp and value. So how do you interpret it? It has to have some context. So different contexts give you a different perspective of that data. Then determining the proper frequency for sensor readings. So again, engine readings versus AC readings or temperature readings, they may not have the same frequency. It doesn't make sense. And if you increase the frequency, you get a lot of data. If you decrease the frequency, you get minimum data. So you have to be very clear what frequency is ideal for you and at what point in time you see that data. Identifying complex patterns over time. So data generates some patterns. One will have to identify and see what patterns are. Figuring out how to handle interactions. This is very interesting. There are devices which operate with each other. For example, a temperature sensor may send you a data depending on certain conditions. The temperature is high or low. And if it is a van, cold storage van, which requires to maintain a specific temperature, you have to interact with that van and adjust the temperature as per the data received. So in this case, there is a time lag between the data received and the data you interact with the van and adjust the temperature. So that time lag is very important. Whereas when you interact with the van at that point in time, the right temperature may not be the temperature you have received. So if you receive temperature at 18 degrees and you want to set it to say 10 degrees, then 8 degrees difference may not be right at that point in time. Then accounting for errors and missing readings. Because these are devices, it doesn't mean they have accurate readings. We get erroneous data. We have to have some algorithms to figure out what are those data and how do we get rid of them. And next important thing is what is the retention of that data? How much time do we keep that data with us? Then there is monitoring. In IoT, the monitoring is at all levels. It's devices, gateways, applications, highly dynamic cloud environments, and everywhere. We have to aggregate information from thousands, perhaps millions of devices on the dashboard. Get insights into device and applications performance and user behaviors as well. Then there are logging. What is logging? Logging is basically the messages put by the developer on a particular event. Maybe error or maybe some information. So why do we require logging? We require logging to trace errors. We require logging to find some information. We require logging to trace out occurrence of some events at a particular time. We have to decide what is to be logged. It is very expensive because of the volume to log certain events and keep it on. Log retention is also one of the key criteria. And the security of devices. Increased number of security threats. The number of devices open so many gateways to the platform. So each device has to be secured. The security in IoT is typically at 4 layers. One is at device layer, then at communication layer, the cloud layer, and the whole security lifecycle management for all of them. Protocol standards. These are some of the protocols listed, are commonly used nowadays. I'll talk about some data protocols which are very important. MQTT is MQ Telemetry Transport Protocol, which is basically used for low-end devices which has lesser battery and lesser processing power. And they are used on the devices like GPS devices or similar devices. CoAP is similar protocol which has constrained application protocol, where the constraint is on the network or on the device itself. AMQP is server-to-server protocol, and WebSocket is a protocol which is most commonly used nowadays to connect to vehicles. WebSocket is the protocol where even a server can communicate with the device. Databases and performance. We have to identify data need for the solution. There are multiple stages where we need data, and each stage the database requirement is different. At data ingest, edge analytics, device manager level, analytics, dashboard, business intelligence, and reports. This is a reference platform which will do data acquisition platform, service delivery platform, analytics platform, and machine learning platform. Platform characteristics would be connectivity to multiple data sources, data ingestion, real-time streaming analytics, process data to big data store, tools for data exploration, build data science models, build applications that consume model outputs, deploy and manage these models in cloud. This is a reference architecture, where on one side there is a machine learning training offline, then the whole platform, and then the database is connected. I'll go through important components of this. There's a Spring Cloud that has ability to connect to multiple databases, builds microservices, and integration with multiple MQs. Next is Apache Geode. This is in-memory distributed database with strong consistency built to support low latency transactional applications at extreme scale. This has horizontal scalability, automatic failover, cloud-ready infrastructure, and seamless integrations with analytics database. On the right-hand side, it's a performance with many other standard caching systems. There is with Redis and Aerospike. LeanPlum is a database that is used for machine learning exercise. This is SQL-based load query, MPP standard, MPP shared nothing database, linear scaling of capacity, loading, users, and concurrency. Analytics-oriented query optimization, write locking, storage, management, and compression is built in. MADLib is machine learning library that supports deep Plum database. Again, with MADLib, big data machine learning for data scientists, algorithms designed to leverage MPP, algorithms to scale as dataset scales, better predictive accuracy for and that uses all data and not samples. These are the references I've taken from. And thank you.
Do we have any questions?
But the operating system of most of the IoT devices, is it going to be predominantly Linux, that is embedded Linux? Because Microsoft also has, for IoT, they have already released their Linux version. So is it going to be the almost 90 to 100% Linux?
IoT devices are Linux variants, so they are not full-fledged.
Yeah, it is a scaled down version, embedded version of a Linux. Almost all of them.
Most of them.
Most of them. Can you tell something about the security, little more about security aspect? Because suppose somebody, a hacker attacks, and you would give an example of a van where the temperature, if somebody switches off the temperature controller, or an oven, he pushes up the temperature, it will be disastrous. So what are the precautions can be taken?
What are the precautions? So the devices communicate with the server on a specific gateway. So those gateways are whitelisted, and only those communication from those gateways are accepted. If it is hacked, then there is encryption layer where messages on the wire are encrypted. And then for increasing or decreasing or sending sensitive information to the device, there are other ways of doing two-level OTP authentication and other stuff also can happen. So when everything happens, then the messages can go. So firewall at the gateway level will make sure that communication happens only from that port and from that device.
Is there a standardized way to create an IoT network? Or basically, like if one company wants to set up their IoT network the way they want without the required securities in place, and the other company would rather want those cyber security at every single level. So is there a standardized way by which we can put all the IoT devices in place?
So to answer this question, what are the devices? If the devices are following certain standards and protocols, then there are Azure or Google or AWS also have their cloud platforms, IoT cloud platforms, which integrate devices into their platform, or which anyway has further security levels built into it. Or otherwise, you will have to build each and every level.
So this is not a standardized way.
It is not a standardized platform so far. So, and secondly, the cheaper devices have cheaper or the less powerful, or they don't have processing power, they don't have batteries, so those constraints come.
So lesser processing power would result in lesser security.
Lesser, you can't encrypt much.
Thank you, Ashish. So our final speaker for the evening, Rohan Verma, over to you.
Hello. Hi everybody, thanks for staying to the end to hear me talk, and thanks to Mansa and the PayU team for inviting me to speak on this topic. Basically, the sessions so far have been so interesting, and they've covered the software side or the non-hardware side of AI and IoT. And although my topic, which I wanted to talk about, is on applications of IoT and AI based on my own experience in the tech world. And I thought that it will be incomplete the full day session without somebody talking on IoT hardware per se. So I invited a really good local Goan company called Ring Technologies, which are doing awesome stuff on IoT hardware, and welcome their CTO and co-founders here to speak on IoT hardware. Then I'll jump back to speak on applications.
Thanks. Hi everybody. Welcome to Soda. I'm from Ring Technologies. First of all, thank Rohan for sharing the stage with us. So today I'll be covering everything related on IoT, which is technology and product design. Okay, so before I go into it, a little bit about ourselves. We started 7 months back in December. Rohan and me, Rohan is the CEO, I'm the CTO. Among us, we have around 30 years experience in the wireless field. Rohan was working with Park, TCS, Motorola, Nokia, Broadcom, RFDSB. He returned last year from Silicon Valley, came back for good. In my case, been working for Motorola, the wireless division of Motorola, and then Nokia acquired it pretty much right from the start through TCS. I was in Chicago,
And 4 years back, I moved to India, and for the last 4 years, before I started this, I was working from Goa for Nokia. You know, so technology. IoT is all about what technology you choose. And this slide will give you an overview of what are the different technologies in the IoT area. So roughly you can divide the technologies, roughly this is how I've divided into on the top left, traditional wireless, 2G, 3G, 4G. This is everything that everybody using GSM modems and all. That's the traditional wireless. Bottom left, local area networks, Wi-Fi is the most widely used. Cameras, Wi-Fi cameras, Wi-Fi doorbells. So that's the Wi-Fi part of it. Top right, something known as low power WAN networks. LoRa, you all must be hearing a lot about it. Sigfox, some proprietary RF technologies, and something I've not put here that's because it's still not deployed in India, which I've been working for the last 1 year in Nokia work. NB-IoT and CATM. So those are low power WAN networks, and then last on the bottom right is personal area networks, Bluetooth, Zigbee. So what are this technology, how do you differentiate between them, So what is important in IoT, when you select a device? A few important things is, is it going to get operated off from battery or does it have power? So power becomes important there. Second thing is it's all wireless, right? You're getting something to the internet, right? So what's the range, correct? Then how much data you are going to send? So the data rates, correct? And finally, and probably the most important thing, how much will it cost? What's the cost of the device? So you'll see over here, traditional wireless, long range, lot of 20-25 kilometers. It has high data rates, but battery life, no, it can't be operated from a battery. Cost is also high of the modules. There must be some of you all who are in IoT must be knowing modules are not cheap, correct? Wi-Fi, the range is very short. Maybe just 100 meters, 150 meters. Mostly it will just be 20-30 meters in a dense environment, correct? Data rates, yeah, very high. So that's why it's getting used for doorbells, video doorbells, then cameras, video cameras. Battery life is low. You can forget about operating a Wi-Fi device from a battery, correct? Last, the cost is medium because it's so widely used. Even though the chip is complex technology, it's still low, medium cost, but it's not low cost. Now, low power WAN networks, LoRa, which has been picking up slowly, the range is long, easily it can make 15-20 kilometers easily. The data rates also are very low. That's a problem actually, but then most of the time, let's say you have in a city, a dustbin, you want to know whether it's full, you're not going to send a lot of data, right? Just a few bytes, either it's full or not full, right? So that's where it is fitting in, battery life, long battery life, cost is low. And a little bit about NB-IoT and CATM technologies. Those is something that is coming from 3GPP. Those are the guys who release the standards for 2G, 3G, 4G LTE. So they said, okay, hey, you know what, we have to address this, right? We have to be in that area, So what they have done is they have tweaked a little bit with their, actually not a little bit, a lot with their technology and all, and they have come up with something known as NB-IoT and CATM. CATM is something which is based on 4G. It works within the 4G technology. NB-IoT is something that works within, works in the band of, within the, like somewhere where there is 2G and all, easily it can fit in. Okay. One of the advantages of NB-IoT and CATM is, you don't have to change the hardware. The hardware is same. For example, I was working with Nokia and I was working on this 4G modems, which were in 2010. And that hardware, we had deployed it in, KDDI in Japan. And 1.5 years back, I was working on NB-IoT, and guess what? We were just changing the firmware of the software, whatever you call it. Those are all software-defined radios. So we were not changing the hardware. It's the same hardware which was, released in 2010-11. We upgraded the same hardware and made it NB-IoT CATM compliant. Okay. Last thing, personal area networks, Bluetooth and Zigbee, very short range, low data rates, but very good battery life. You can, just operate the sensors and everything on a battery for example, for Bluetooth and all for 3, 4, 5 years based on what's the frequency of data you require. And cost is very low, very, very low cost. Because Bluetooth, especially the chips are very cheap, Now, the range is very short here, but there's something, I don't know if you have heard about, there's something known as Bluetooth mesh. And there's also something known as thread. Just 2 days back, there was an article that Apple is also pushing thread. They have also come on the bandwagon of thread. There was Google first, and there was Amazon. Now there's Apple. So thread, mesh, these are the ones they are addressing the range problems of personal area networks. So most of the time, what happens, right? We have a lot of sensors in an environment. So you don't have to have the range, a lot of range. As long as one of your nodes can pick up the data from the other node and pass it on to the next node, your range problem is solved. So the mesh network is basically addressing this range problem of Zigbee and Bluetooth. So that's about technology. So this next slide is the general architecture of IoT. So as I said, you have the cloud, and you have on the left hand side, you have the home and industry network, So you have Wi-Fi, which directly connects to the router, and then in the bottom over here, you have the Zigbee proprietary RF, which are nothing but sensor nodes to which it connects to a IoT gateway, and from the gateway it will go to the router. From there it will go to the cloud. Okay. Then you have your LoRa, then Sigfox and everything, where the data goes from the sensors to a gateway, and from the gateway it gets connected to the cloud using 3G, 4G or 5G. And then finally you have your traditional cellular network, where usually what we used to send, from sensor we used to send the data direct to the base station. And before that, batteries were, because of the battery life of 3G, 4G modems, you could not do anything. But now, with NB-IoT coming in, you'll be able to actually put, sensors and all, which you can run on batteries and then directly connect using the cellular network to the cloud. So one thing I would want to point out here, you see LoRa and NB-IoT kind of are similar, but you don't know how it will pan out. NB-IoT is still not come out. But the way I feel is LoRa works in the ISM band. It's a free band. So there's a chance that LoRa, we feel, will pick up in the rural sector, whereas NB-IoT, CATM and all will be used mostly in the urban sector where there's dense environment. So dense environment and all LoRa might not work because, you can't have everybody publishing. Everybody sending data, you're going to have all sort of congestion. It won't work for anybody, A rural network where there's not that much congestion and all, wide spread out areas, it's going to work. So something that we are working on LoRa. Also, we are just waiting for the NB-IoT network to get deployed in India, after which we will basically start working on it. The gentleman before me already covered, I think, the software, so I won't go too much in depth. Just MQTT, CodeUp, HTTPS. HTTPS, most of you all must be knowing. That's what the GSM modules do, right? Get and post. CodeUp is something new that's coming up. It uses, instead of TCP, it uses UDP. And for security, it uses DTLS. MQTT is the most widely used right now. AWS IoT uses MQTT. It's basically based on subscriber publisher architecture. Works on TCP, uses SSL, TLS for security. The same security that is used when you do payment using your credit card. TLS 1.2 is what is supposed as the best security right now available. Okay, so it's about software protocols. The next thing I wanted to cover, how do we go? So we are a very much hardware centric company, So how do we go designing our hardware? First, we do a requirement analysis. Okay, so what do you mean by requirement analysis? We go to a customer site and see their network. What is your problem? Everybody knows that, okay, you have to solve a problem, correct? So we look at okay, where do you have to solve the problem? What is the environment? Okay, it's a factory. Okay, how big is the factory? Are the power points available at what distance? Okay, where do you want to put the nodes? Do you have existing networks like Modbus, CAN bus? Do you have to, you don't want to change those things, right? Okay, can I just take the CAN bus data and put it on the, on a Bluetooth or, Zigbee network, Then are there a lot of metal structures, how will it affect my wireless environment? You do all that kind of requirements analysis. After that, you come to the architecture design. Okay, so based on what you have found out, what is the customer environment, what he wants to do, okay, how do I go about designing the architecture? What technology? This is the part where I select the technology. What is the cost for that technology? Because each technology has a different cost associated with it. What is the cost to the technology? So once you've selected the technology, then you go and decide on the components. Probably the most important part from the cost perspective. Okay, what are the components I'm going to say? Which is the IC I'm going to select? Okay, with that IC, what is the development framework? But today, it's not like before where you can take 1 year to develop. You have to develop a product within probably 2-3 months, correct? What is the existing, are the evaluation boards available? Are there libraries available for that, IC? So yeah, once we have selected a component, then you do something known as proof of concept. Is it doable? What are the evaluation boards for that IC, Get our firmware guys, our software guys on it, with some hardware guys. Okay, prove the concept, probably in 3-4 weeks, prove the concept and see if it works, the concept works. Only after that, then we go to the hardware design. Okay, so you'll do your hardware design, you'll do your schematics, layout, everything, all those things, Then for firmware, software design, again, it started with the proof of concept. Over here, you do it for your specific hardware you're designing. Then you do prototyping. Order the PCBs, get in it, manufacture the board, see if it is working, how it's supposed to work. If it's working, do integration, board bring up. One of the most difficult things in hardware design, board bring up. First time getting it working, Then integration testing. Once integration testing is done and everything is working fine, then you go to manufacturing. Never go to manufacturing before prototyping, Usually, we get manufacturing within 2-3, by the second prototype if you're lucky, otherwise third prototype will be your manufacturing phase, Then after manufacturing, system level testing. You test it for everything that is supposed it is designed for, and then product certification. So product certification, EMI, MC compliance, something known as highly accelerated life test will tell you how well your product will perform. Is it a very robust product? HOS, highly accelerated screen, testing basically will tell you, how good is the manufacturing process is, because most of the time you are not going to manufacture, somebody else is going to manufacture it. Is it a good manufacturing? Will it break in the field? Those things. And one of the most important things in this is supply chain and vendor development. So like, okay, what are the you have to develop here. From day one, we started on our supply chain. Who are our suppliers going to be? Who are contact them, talk to them, find them, vendor development. Visit their factories, go and see how they are. Do they have proper manufacturing processes in place? So this is what we go through, and this is basically the hardware product design process. So yeah, so that was about technology and hardware design process. Yeah, now I'll hand it over to.
So a little bit about myself and my experience and why I should talk a little bit about IoT and maybe AI. I'm an electrical engineer from Stanford and I'm CPA from London Business School. I'm a director at MapmyIndia. It was started by my parents in the early 90s, and I got involved in 2004 when I was still in college, and basically led product development and technology, as well as some other things like marketing and corporate strategy. And we are a leader in maps and location technologies in the country, including GPS-based IoT devices and platforms. I'm also an investor in Visit, which is a startup focused on the health space. It's an AI-driven health and wellness assistant. So I've gotten a chance to kind of see how a startup is building a AI product that can really revolutionize healthcare, and that's their sincere effort. Just recently, in the last 1 year, I got the itch to start something from scratch and learn that process, because second generation in a family business, you don't learn that part. So I started my own startup called Infidreams Industries. It stands for Infinite Dreams, and it's a mission-driven tech company. And basically, I'm building an app called the Infidreams app, and I'm building these systems called InfiShakti. So, what have we done with IoT and AI thus far at MapmyIndia and then at Visit I'll talk about. At MapmyIndia, basically, we focused a lot in the last maybe 8 years on building an IoT platform that can scale up and support the automotive, transportation, logistics industries in the beginning, but then has ventured out into supporting a myriad of IoT devices, applications, sensors, etc. So we built an engine, we built APIs so that anybody can hook into our IoT cloud, and we built SaaS and apps on top of that, as well as we allow anybody to bring in their apps or SaaS and integrate. So really go-to-market for IoT becomes very easy, as well as you can leverage MapmyIndia's kind of sales organization. It's a $250 million company, so it has 5,000 enterprise customers across the country. And so it really is a really quick go-to-market for any application or device. We also do GPS-based IoT devices for tracking and connected car. We don't yet design and manufacture our own hardware, we spec it for applications. And the third thing, which will require pretty much every technology that's out there, is about 3 years ago I gave the team the challenge that we've been building maps from scratch for the last 25 years with 750 people, lots of survey technology. And I said that, okay, it's not just good enough to have the best map of India currently, but we have to build a map so advanced, so accurate, so detailed, that it can power self-driving cars. And just by pushing ourselves to the limit of technology of mapping, a lot of applications will happen. So just to give you a sense of kind of the IoT platform, it's called In Touch. It allows basically IoT devices to be in touch with not just the cloud, but you as users. And you can integrate all sorts of devices, be it vehicles, people, assets, any sorts of device to the cloud through APIs at different levels of abstraction. There can be n number of applications you can do. So of course in the traditional GPS tracking, GPS telematics, connected car applications, but also smart city applications like solid waste management, street lighting applications, indoor positioning applications. So this is kind of our partnership model where we build this engine, and then IoT device makers, IoT application makers, they kind of hook into this cloud and leverage all the content underneath for interesting analytics that you can use using maps. And as we are mapping not just the outdoors but the indoors as well, you can kind of give location context outdoors as well as even indoors for indoor sensors and IoT devices. These APIs are freely available for developers to kind of use. They just go to mapmyindia.com/API and they get telematics and tracking APIs, as well as they have maps, navigation, tracking APIs so that they can build whole-scale applications, and then the custom APIs and custom location-based data that we provide to people. And these are just some of the sensors that are there. And how do we package this up just so that the power of this technology can be in the hands of consumers as well? This app that we're working on called the Map app, it combines not just maps and navigation the way Google Maps has, but also tracking your loved ones, your devices, and you can stay connected as well and get interesting location analytics for your own data as a consumer. So you see here kind of people that you want to track. These could be friends, colleagues, etc. the devices that you want to track. They could be your car, a GPS device in your car, they could be your vehicles, etc. So all in one kind of app as just a showcase for how all of this put together works. And this is on basically the application of AI and IoT on maps. We know self-driving cars is a cool technology, but it's also super useful because of accidents, as Richard said. And essentially, to be able to build a self-driving car, you have to have an intelligent map, an advanced map, which recognizes objects as well as in real time and tells you kind of how to avoid obstacles. So we combine outdoor mapping with indoor mapping in 360 degree using 360 degree cameras, 3D using laser scanning or LiDAR, and we make it live using IoT, using telematics. So we stream this data back to our servers, we process it, apply AI, machine learning, etc. to try to build this, what we call real view, which is a digital map twin of the real world. In Industry 4.0, you know this concept of digital twin or digital manufacturing, and we want to apply this to the real world. We want to build a model of the real world, and we call that real view. And we think that map will be quite advanced. And so this gives you a sense of like an AI and IoT powered advanced map. Not just does it know the roads, the places that you want to go, the houses, but it also knows, it gets data real time from civic sensors or IoT sensors in the real world. There are sensors on the cars which can detect objects, detect obstacles, detect live obstacles like pedestrians, etc. And this information can then be shared amongst different vehicles or different systems so that everybody's kind of updated on this self-updating real view of the real world. Yeah, this kind of tells you the different steps it takes to build this. I had thought that we will build this digital map twin or real view in 2 years. Obviously, it's going to take a few more. But we're well down the path. We're doing 3D laser maps. We're doing 360 degree indoors. We're now doing advanced video maps, and we'll get there soon. So the next experience is on what I've seen with Visit, building a AI assistant. This is things like a natural language understanding and a chatbot, AI-based triage of health conditions and symptoms, and integration with health wellness, IoT devices like a Fitbit, etc. So what is Visit? It's a personal AI-driven health and wellness assistant. Essentially, these are the things you can do in the app. You can check your symptoms, talk to a doctor, log your meal, health, monitor your health data, do health risk assessment, order medicines, etc. And it's a chat interface. So you're going to chat with this the way you would chat with a doctor or talk with a doctor. You can even consult on the phone, but that's not AI driven. The chat part is increasingly AI driven. And just to give you a sense of kind of what you can ask, so hi Ravi, happy to help. Just saying hi or try asking these questions. So it's kind of telling you what all you can do. I'm having a severe headache, I have pain in my right shoulder, what is this, what are symptoms? I feel low, I have constant back pain. And then so that's a one interface for all health queries. And it'll give you generated suggestions to the platforms. This is what you can do with AI. And so essentially you're having a conversation. And they're trying to triage the symptoms that you say so that it can basically increase the productivity of a doctor, of a specialist who has to deal with. India has a general shortage of doctors, so on and so forth. So they're trying to solve that problem by leveraging AI. And then the doctors actually can train this AI to keep getting better. So we learned a little bit about reinforced learning in the earlier session. So this is just one example that when kind of the patient or the user says this, my throat has been itching, blah, 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 the AI can come up with these possible 3 suggested responses. That's what it thinks. But the doctor can then kind of ratify which of these options is kind of the good option for this input and actually make some edits also. So that's how this AI is then applied in the real world context. So that gives you a quick kind of overview of how AI and IoT, at least my experience with this so far, and kind of how to put it together, something interesting. Again, you're chatting with the AI, you need to find something. It leverages MapmyIndia's maps, but not just that, if you're in an emergency, it actually hooks into the IoT device and then you can track them. So it's so cool that when technology progresses to a certain level, it experiences which were earlier impossible become possible, and I mean that's what we are in tech for business for, at least I feel. And so what are dreams for the future? So about 8 months ago, I said, this is great, everything is good, MapmyIndia is good, visit is good, but I have an itch. First itch was, I have a dream, like many people. My dream has always been this mission to make the world better, and I kind of thought with this app I had kind of fiddling around in my head, I wanted to bring it to life because I think that can help. I'll tell you about it. And the second thing was, it was not just a lark, it was real. My wife was hyperventilating every Diwali in Delhi because the pollution was so bad and our 2 young kids would eventually have to breathe that when they go to the park. And she said, let's do something about it. Her point was, let's move. My point was, let's build some technology to solve this. We've done both. So we moved to Goa 5 months ago and it's been amazing. We love it. We live in Bandyopadhyay. And also I'm building these Infidreams systems. So I'll tell you about that.
Don't go to Vasco, full of coal gas.
Yeah, I live in Bandyopadhyay, it's amazing. And most of Goa is amazing actually. So what is this app? I really say that this app can help all your dreams come true. And like, what does that mean? And why is that important? Because I think everybody either should or does or should dream. Because dreams help us visualize a better future, inspires us, motivates us about the time to come. And so if you look at the app, this is kind of a prototype. It's on testing on iOS. You basically can write and see all your dreams in one place. And this is kind of nice because every time you see your dreams, it gives you a reason to live, to be happy, to get excited. And these can be dreams, goals, missions, objectives, aspirations, personal, professional, social dreams, like I dream of clean air. And then as you dream, then you start thinking about, what are the to-dos needed to make those dreams come true? This plan of action is the first step to achieving your dreams. So essentially you write this to-do list and then you can track kind of how you're progressing against it and get reminders. And finally, this aspect already that's there is this diary, because you don't start dreaming, you have to start introspecting, then have to take a step back. And this daily purpose, daily objective of like introspecting gets you kind of step back and think. It's actually, that is the life-changing experience of this app, this diary. But not just that, we don't know everything about how to achieve our dreams, whoever we are, because our dreams keep getting bigger. So we need to ask for help. So there's this discuss section where you can start asking for help, not just from your trusted people who can feel comfortable sharing your dreams, but you can be connected to expert coaches in certain areas, be it a health coach, a financial coach, a counselor, whatever. And you can have discussions with them about how to achieve your dreams. What are the tools needed? They can advise you. And then if you have to get certain things done which you cannot do yourself, that's what the app will allow. It's confidential, private, secure, it's free. My only objective in making this is to help everybody. It's not the business side of what I want to do. There's no ads, nothing. That's all bullshit. What happens with what people do with data? This is for you to use. It may just be offline but connected for services. But yeah, I think that this will help everyone make their lives better and in turn make the world better. So what's the use of AI and IoT in this? So right now the app is kind of dumb, to be honest. I mean, you tell it, it's like your own brain, like written down in a digital diary. But using AI, it can actually start having intelligent conversations and cognition. So it can serve as a 24/7 available concierge and a coach that helps people achieve their dreams, get things done, and connect with experts. So like chatbot capabilities, kind of what Visit does. AI able to intelligently match users to expert coaches, kind of what CodeUp tries to do when you ask a question, beyond your own contacts. Possibly interfacing with IoTs to get certain things done efficiently, because we're talking about achieving your dreams. I want to like exponentially increase human potential and capability. So things that are mundane need to be done quickly. So if you can, I don't know, if it makes you more comfortable that lights are off when you come home, that it's possible to do, but in this context it becomes interesting. There might be other possibilities and I'm open to suggestions. This is an app for everybody has a say in what goes in it, etc. So that's what I think is going to be there with the app. The second thing is around this clean air, which really bugged me a lot in Delhi. It probably bugs a lot of people everywhere in the world. And so I said that, I hate pollution, it does nothing for anybody. Of course, it's great that electric vehicles are coming. This is good. But what about the 210 million existing dirty diesel, petrol, and CNG vehicles on the road in India? That's 21 crore vehicles. I think Goa is almost like 10 lakh or 14 lakh vehicles for 14 lakh population, which is ridiculous. That's all the pollution that's out there. So I want to convert existing vehicles to electric, to zero emission, essentially. You remove the IC engine, you remove the fuel tank, and you put in a motor, you put in a controller, you put in a battery. It's simple in thought, it's complicated in implementation, and it's regulated because it's a car that drives on the road and can cause accidents. So it's a bit of a hard technical challenge, but we're on our way to solving it. Whatever argument people had around that EVs are powered by coal, finally because it's getting charged by the grid, well, okay, I want someone to provide those clean energy systems so that we close the loop on, and then it's called well to wheel, not just tank to wheel. Well to wheel is clean energy. And so why? Because I dream of clean air for my kids, for all of us, for myself, but also it's a good tech and business opportunity. It's essentially the future of mobility, energy, and society needs to include these types of systems, and I'm kind of focused on building this out quickly. So this is kind of a picture of how that scenario would look: electric car, motorcycle, nothing fossil fuel powered, solar, wind, happy people. What are the AI IoT uses for these, for example? Well, Infidreams is all about maximizing and optimizing sustainability and efficiency of natural resources to meet the growing demands of mobility and energy across society. It's like a whole, it's a lot of words, but basically, as technology improves, our demands on technology improves. So as computing became cheaper, we wanted more computing. As ride sharing came, the number of miles or kilometers being driven has increased substantially. Well, in the case of computing, I don't think it's had like a bad impact because they've started making data centers which are clean energy powered. But in the case of ride sharing, it's terrible impact. It basically means more congestion and more pollution. So, we need to maximize and optimize that. Besides the core electrification and renewable energy generation technologies, IoT and AI will be critical to help with this maximization and optimization objective. So basically, if you want to replace 210 million dirty vehicles with the equivalent number of electric vehicles, you're going to have 210 million vehicles which are scrapped. So basically, you wasted 210 million vehicles worth of like steel, metal, and like perfectly working bodies, just terrible like internals. So it's not an optimal resource usage of natural resources, which are scarce. So we need to kind of keep them going for the future generations. So some of the uses of AI, IoT, and like you can apply this from all the techniques and technologies and algorithms that people talked about in the first set of sessions. Remote monitoring of electrified vehicles and energy systems parameters. This is like vanilla IoT. You can apply this to EVs and clean energy systems. And basically in EVs, to optimize usage of scarce fuel resources like the battery, you basically can start using AI and ML to go beyond the standard A-star algorithm that for routing, which is like time or distance. But you start factoring in gradients of the nodes and the powertrain demands. So basically what causes minimal energy costs, and you can kind of learn this over time as well. And like you can avoid traffic because traffic causes more consumption of energy, etc. In the future, intelligent transportation systems will help minimize congestion and accidents. They'll also require significant levels of IoT and AI integration, like civic sensors, to connect them to command and control centers, to then intelligently drive traffic infrastructure in vehicles. So you can imagine that traffic lights should switch on and off more dependent on the local environment rather than kind of just preordained. So this is IoT plus AI combined. I think this will happen later, but the smart grids which self-balance, which balance energy needs and power backup, not just a centralized grid, but like a distributed generation of electricity. Because remember, EVs have big batteries, and that's like better than a diesel genset, to be honest. So like first of all, we can remove those diesel gensets and put EVs in place, and then we can use the EVs that when you're not using that vehicle, it complicated and like it's hard to wrap our minds around how we would do that manually, but using AI probably will get better. And yeah, this last is, once we've got this fundamental right around electrification, which is zero emission mobility, then we should actually push the envelope on ride sharing and asset utilization, because it's like then computing the marginal cost and marginal negative externality of driving kilometers is zero essentially. No pollution and very little cost. Then you drive up the ride sharing concept and then you need AI. So anyway, these are some of the things that I thought of sharing. I think the guiding principle behind everything I do at Infidreams is that all our dreams can come true, and what I do generally is around that the world can be made better. It requires a lot of work, it requires a lot of green tech. Technology is becoming stronger and powerful, and essentially, as I think Richard said, we're putting our own human mind into that algorithm, and we're seeding that in the AI, and then we're getting it to learn based on data. So actually, it's no longer just that we have to be engineering-wise correct. We don't just have to have the intellectual honesty, but we have to be human-wise correct. We have to have the moral honesty or moral compass that how we guide these technologies on AI or IoT is for the good. And we can't just say we're building great platforms. We're seeing what's happening with Facebook and other things. There's huge negative externalities. So just because the IC engine was convenient doesn't mean it should have been popularized. We should have stuck around with EVs, even do some short-term pain. So anyhow, that's what I'm trying to do with Infidreams, like do something good while building a big business. And yeah, looking for people to go across tech. So forward to kind of talk. So thanks a lot, Hans. I hope this was useful as an application.
Thank you, Rohan, and thank you, Man. So before we close, a quick minute to announce our puzzle winners. We have. Okay, I have it. So yes, do we have Anantacharya? Yes. Tanushri and Salvino. So if you can just, Tanushri is over there, Salvino. So just so you all know, this is, we just select the highest number of words and we do it as like, we just pick up out of the lot. So it's no bias here, okay? And yes, so thank you guys. Okay, thank you guys for coming today. Thank you for making it such an interactive session. We never expected such a great turnout, and this makes us want to come back more with better and always even a better setup and okay, that everything that you might need from us in these sessions. So we'd love to hear if you have any feedback. We are very grateful to our speakers, Ashutosh, Richard, Rohan, Malcolm, Ashish, Utkarsh, and Anubhab. Thank you guys so much for joining us today. We are going to give them we have a little goodie bag for them. So a round of applause while we give it to them, please. So yes, if any of y'all are looking for a payment gateway, you know who to reach out to. We'd be happy to help you all out. And a special thank you to Rohan from Prototyze for introducing us to maximum number of speakers who we have been able to reach out to, and 91 Springboard as always. Thank you guys once again. We have burgers and soft drinks for you guys on this side. The speakers are here. Richard had to leave, but if you guys want his email ID, I'd be happy to share it with you all. You can always contact him. Thank you all once again and have a good night. Thank you.